All right, it's 5:30 Monday, July 20th, 5:30 p.m. and it's time to get started. We are going to finish up chapter 11 today, and that leaves next time working on chapter 14, possibly a little bit of 15 as well. And I might have enough time to do 15 again later, but I might just have you watch one of my videos, or I might actually have time to fit it in class or something like that. So, anyways, keep an eye on your emails, that sort of thing. I did just send you an email about tomorrow morning's lab. We normally meet at 8 a.m. on Tuesdays and Thursdays for lab, but we're done with our labs. I hopefully will have some more labs graded for you tomorrow. I actually have couple labs already graded, so I just need to put the grades in. But other than that, I'll post them tomorrow, and hopefully maybe even more than a couple more labs done. But the 8 o'clock meeting tomorrow is completely optional, but it's a student Q&A. I say completely optional. I am going to be there at 8 a.m. because you guys paid me to teach you, and or I say you paid the school for me to teach you. So I am here for you guys, whatever time you wish to show up. But I will come in at 8 a.m. and just have a Q&A session for anybody that has any questions. If I log on and no one's logged in by like 8:15, 8:20, then I'll just log back off. But if you tell me, hey, I can't make it until 9, or hey, I can't make it until 9:30 or something like that, just send me an email or send me a text message would be preferred, and let me know that that's the case, and then I'll make sure I stay on until then, or I'll log back in at that time. So just let me know if there's a time that you want to do. Technically, you're supposed to get me from, for basically a few hours. Uh, well, it's over 2 hours anyways, that you're supposed to get me. So anytime between 8 and 10 a.m. that you would like me to meet you, I can do that. So just send me an email and let me know, or text message is preferred, and let me know which time you actually will be able to make it in, and I'll make sure I'm there at that time. But like I said, if I get there at 8 a.m. and nobody's there, I'll probably wait 15, 20 minutes. And then if nobody's still there, I'll leave. But again, if someone told me that they're coming, I'll make sure I show up. And I also sent in an email a few minutes ago letting you know that if y'all have some other times on Tuesdays or Thursdays or Fridays, I can do another Zoom session to have a Q&A for, again, course materials or course policies. So make sure you do that. And we're going to go ahead and get started in chapter 11, which I've already covered the equations for and give you a little introduction to, more or less. So now we're just going to start in on the examples. So let me go ahead and share my screen with you folks. Hopefully it'll pop up in a few seconds. Looks like it's coming now. Again, if you're watching this and you're in my class, it's highly recommended that you go ahead and log into the ebook and look at the examples that I'm going through as I'm going through them. I still try to give you as complete a picture and description as possible, but still, it might be best if you have it so you can refer back and forth to it as I'm working the problem. So we're starting off with example 11.1, and we're going with object rotating on a string of changing length. So hopefully I've done this before. I know I used to take, like a mass on a string, and you would hold the mass on the string above your head, but then you could take and grab the end of the string, and if you pull it in a little bit, what you'll see is as you're pulling it in, the mass starts speeding up and up and up and going faster and faster. That's a ramification of conservation of angular momentum, and that's pretty much what's going to happen in this problem. It says a small mass m attached to the end of a string revolves in a circle on a frictionless tabletop. Excuse me. On a frictionless tabletop, the other end of the string passes through a hole in the table. Initially, the mass revolves with a speed of v1 equals 2.4 meters per second, and a circle of radius r1 equals 0.80 meters. The string is then pulled slowly through the hole so that the radius is reduced to 0.48 meters. What is the speed v2 of the mass now? So we have a mass that's actually at some distance away, and if you treat it as a point particle, and you use, for instance, the parallel axis theorem, you'd see that a point particle should have no moment of inertia about its an axis through its center, because its center is its whole body. There's no radius to it whatsoever. So that moment of inertia about the center of mass is zero. The moment of inertia about a parallel axis would be equal to that moment of inertia about the center of mass, which is zero, plus the mass times the distance the mass is away from the center of mass, times that distance squared. So mb squared basically, or mr squared. That ultimately results in the moment of inertia for a point particle just being mr squared. So that's what we're going to use here. Here's our solution for this one. So solution, remember I normally start this off by giving some equations. So the in this case, since it's frictionless, we can assume there's no net friction acting on, or no net torque acting on the system. And when there's no net torque, we know from the rotational version of Newton's second law that no net torque means no dl dt is equal to zero. And if dl dt is equal to zero, then that means L, the angular momentum, is a constant. And if L is a constant, that's the very definition of conservation of angular momentum. So what we're saying is L1 is equal to L2, which implies I1 omega 1 is equal to I2 omega 2. And I want to point out that for this particle, I is equal to mr squared for whatever the radius is going to be. So with that in mind, I'm going to go ahead and say the moment of inertia initially is given by m times r1 squared times omega 1, but we're also going to make use of the fact that V is equal to R times omega. So that means omega is going to be equal to V over R1 for omega 1. And then after we pull the string in, we're going to have M times R2 squared times omega 2. But again, we're going to use the V equals R omega. We can already see that the masses cancel out, so we can go ahead and do that. But now we're going to get R1 squared, and then this is going to be V1 over R1 is equal to R2 squared, and then this is going to be V2 over R2. And you can see in this case that the R is going to cancel out one of the exponents, and we're just left with R1 V1 equals R2 V2. And with that in mind, we can solve for V2. So we say V2 is equal to, obviously that's going to be R1 over R2 times V1. And now we just plug the numbers in. R1 is 0.80 meters, and R2 is 0.48 meters, and V1 is 2.4 meters per second. And notice this is basically the drawing of the figure here. There's the little hole. We got the string out at a radius R1. We're going to pull it into a radius R2, and it's going to speed up. So this should actually give us our velocity. And when you multiply point eight times 2.4 and then divide that by 0.48, that gives you 4.0 meters per second is V2. So that's what conservation of angular momentum gives us for when we pull the mass in. It goes from 0.8 meters to 0.48 meters. It speeds up from 2.4 meters per second to about 4 meters per second. Do give that a try at home. Of course, don't use too big of a mass, and don't do it next to a window or a TV screen or a computer screen or something like that, because there is a chance that when you're spinning that mass and it speeds up, if you pull it too far, it'll actually speed up so fast that the string will break, and that could, of course, become a projectile that could harm you. So be careful with it, but I do recommend as much as you can to experience these things if you haven't already experienced them. So now let's go to example 11.2. This is about a clutch. And it says clutch. A simple clutch consists of two cylindrical plates that can be pressed together to connect two sections of an axle as needed in a piece of machinery. Excuse me. The two plates have masses MA equals 6.0 kilograms and MB equals 9.0 kilograms with equal radii. R0 is equal to 0.60 meters. They are initially separated. Uh, Plate MA is accelerated from rest to an angular velocity omega 1 equals 7.2 radians per second. In time, delta t equals 2.0 seconds. Calculate A, the angular momentum of MA, and B, the torque required to have accelerated MA from rest to omega 1. Next, in part C, it says plate MB, initially at rest but free to rotate without friction, is placed in firm contact with the freely rotating plate MA, and the two plates then rotate at constant angular velocity omega 2, which is considerably less than omega 1. Why does this happen, and what is omega 2? So that is the question here, and I forgot to write omega 2 equals question mark and y. That's what we're trying to solve here. So solution, we're again going to have angular momentum is conserved because we're assuming, as we were told, that these things are on frictionless axles, so the friction should be uh, basically very close to zero, and that's really the only force that could be applied to either of the individual discs by anything other than each other. And of course, the discs can apply forces to each other because what we're going to consider the system to be is mass MA and mass MB. In other words, each of the clutches together consists of or make up the actual system. So the system is the plate MA, and then above it the plate MB. That's the whole system. And of course, initially just MA is moving, but after the fact, MA and MB will be moving. So let's start off with L1 equals L2, and that means I1, excuse me, I1 omega 1 equals I2 omega 2, and we're also going to realize that since these are cylinders, we're ignoring the actual axle shaft up at top. Obviously, you can see that even if that thing's kind of heavy, its radius is so small, it's probably not going to be a marked contribution to the moment of inertia of it. So we're just going to treat the moment of inertia as if it's a moment of inertia of a cylinder. I don't know why I keep yawning. Sorry about that. So I1 equals well, I'll just say I instead of I1 because it's a general formula for cylinders. So I'll say I cylinder. How about that? Is equal to 1/2 m r squared. And that's what we're going to go with there. Now we can say for part A, we're trying to figure out what the angular momentum is. And the angular momentum, of course, L sub A, which is what we're looking for, is I sub A times omega that we actually have, and I called that omega. That's the 7.2 radians per second. So what we're going to have is 1/2 times the mass ma times the radius ra squared times omega. That's 1/2 times the 6.0 kilograms times 0.60 meters squared times 7.2 radians per second. And that's the angular momentum beforehand. Now we can calculate all this. We're going to say zero point 0.5 times 6 times zero point 0.6 squared times 7.2, and that's going to give me 7.776. So I'll call that 7.78. And the units are kilograms meters squared per second. Notice I've dropped the radian, and I should point out that this is in fact the standard unit for angular momentum. It's kilogram meter squared per second. We've never made anything special unit out of that. So that is the LA that we're asked for, and of course we only had two sig figs, so that's why I underscored the 8 because that one's not a sig fig. So that's part A. If there was somebody here, I'd ask if anybody had any questions, but there's no one here, so I'm going to just keep plodding along. Now let's do part B. So for part B, they want us to know or want us to calculate what torque would be required to create this angular momentum. And what we can use in this case, and I didn't write it up with a solution, but basically we're going to use Newton's second law for rotation, and that is the summation of the torques is equal to, there's a couple different ways you could say I times alpha, but in this case I'm going to say dl dt. Okay, and that of course is approximately equal to the change in momentum over the change angular momentum specifically over the change in time. I'm going to use that version, and what we're going to do is calculate the change in momentum, which is L final minus L initial, and all that'll be over delta t. So L final is equal to the angular momentum that we just calculated, or actually, let me say delta L instead of us calculating L final, we already did that. We're going to say delta L is equal to L final minus L initial. And of course, we found that L final was 7.78 kilograms meters squared per second. And L initial is zero because it was at rest. And then all of that happened in a time of 2.0 seconds. So, I shouldn't write that yet because I didn't say I was calculating delta L over delta T. I said I was calculating just delta L. So now I need to go back and do delta L over delta T. So therefore, delta L over delta T. Now notice this is all going in place or occurring sort of in a one dimension or a two-dimensional plane, and that means the actual angular momentum vector, which we'll learn in the next subsection, is perpendicular to that, and it's really just one dimensional. It's either going to be pointing up or pointing down depending on the direction of rotation. So I don't need to really deal with the vector symbols. So that gives me that the change in angular momentum is 7.78 kilograms meters squared per second, and that's divided by 2.0 seconds. And of course, delta L over delta T becomes 7.78 divided by 2, and that gives me 3.89. And that is kilogram meter squared per second squared, which remember a kilogram meter per second squared is a Newton. So a kilogram meter squared per second squared is a Newton meter, which is the units of torque as we expected. So that's the actual torque that they asked for in part B, and we have that now. Now in part C, they want us to imagine the two things collide. This is where we're going to use the conservation of angular momentum. So conservation of angular momentum is the following. So C, L initial equals L final means specifically we're going to have, actually let's not use the equal sign there. I'm going to use therefore 7.78 kilograms meters squared per second is equal to L final. Now, what's going to happen in L final is we're going to have basically two disks that are sandwiched together, and because they're sandwiched together, their moment of inertias add together. They're not vector quantities, but they just add. So you have 1/2 m r squared. The r's are equal plus 1/2 m r squared. Again, the r's are equal, but the two masses are not. So we can actually write that as 1/2 ma plus mb times r0 squared, and all of that is going to be multiplied by what we called omega, uh, actually, what we called omega 2. So with that in mind, we can go ahead and plug all this in. We're going to say 7.78. Notice how I am carrying one extra digit. That's how you should do for all intermediate calculations. Why, in other words, calculations that are not necessarily the final answer, but when you have to use a number that was maybe a previous answer but is not the answer you're going for, then you're supposed to use that previous answer or that number to one extra sig fig to do the calculations, and then you can round the result again. So that's what I'm doing here. That's going to be equal to 1/2 of 6.0 kilograms plus 9.0 kilograms times r0 squared, which is 0.60 meters. That quantity is squared, and that's going to be times omega 2. So we can say omega 2 is actually equal to 0.778 kilograms meters squared per second divided by this other unit, which let me calculate the number real quick. The number is zero point 0.5 times 9 plus 6 is 15 times 0.6 squared. And that comes out to be 2.7, and that's kilograms meter squared. So I get 2.70 kilograms meters squared like that. So you see that the kilograms meter squared cancel out, and I just get reciprocal seconds. But the radian, which is a pure number, it's really a S divided by an R, both of which are measured in the same units, like meters over meters. So a radian is a pure number. But all I have to do is take the 7.78 and divide it by 2.70, and that gives me 2.88. But that second eight, of course, is not a sig fig, and that's radians per second because we're allowed to throw that radian in there. And that's it. And the reason for this, of course, is conservation of angular momentum. The total momentum of the system before the two come together is the angular momentum of mass mb, which is 0, plus the angular momentum of mass ma, which is the 7.78 we calculated. But afterwards, they're going to slam together. That's going to cause the a larger mass and therefore a larger moment of inertia with the same angular momentum. And the angular momentum is I times omega, but I just got larger. So that means omega is going to have to get smaller for it to still be the same quantity. And that's the reason why it slowed down to 2.8, which we'd round to 2.9 radians per second. Again, I would ask if anybody has any questions, but there's nobody here today. And that does look like the same answers the book got. So we'll move along to example 11.3, which is an estimate problem, and it's about a neutron star. It says neutron star. Astronomers detect stars that are rotating extremely rapidly, known as neutron stars. A neutron star is believed to form the inner core of a massive star that collapsed under its own gravitation, so a star of very small radius and very high density. Before collapse, suppose the core of of such a massive star is the size of our sun, so its radius is about 7 times 10 to the fifth kilometers, with a mass about 2 times the size of our sun's, and is rotating with a frequency of about one revolution every 100 days. That's comparable to our sun, for instance. If it were to undergo a gravitational collapse to a neutron star of radius 10 kilometers, what would its rotation frequency be? Assume the star is a uniform sphere at all times and loses no mass. Now, this might not lose a lot of mass, but in general, when this process goes on, it does tend to lose some mass. But it turns out in the end of a star's life, this is one of the end results. If it's above a certain mass, then which our sun is not, our sun's likely going to become just a white dwarf. But if you go to an even higher mass, which is on the order of 2.5, 3 times the solar mass. If you have a star that large, then the gravitational force is big enough that when it runs out of fusing hydrogen into helium in the core, because there's no circulation mechanism that allows more hydrogen to come in, what's going to happen is it doesn't have the radiation pressure blowing out as the hydrogen starts to run out. So the gravity is going to crush that. And if it crushes it to a high enough temperature, then we can get another level of fusion going. It can actually start fusing helium into carbon, for instance, and some other things. But if that continues on as you run out of then helium, and then you run out of whatever it fuses to next time, which would probably be carbon or something like that. You could actually go through several different things that's going to fuse, and the end result can be either like a neutron star or a black hole or a white dwarf, or excuse me, a white dwarf would be smaller than that, or a supernova explosion. So we're handling the case where it becomes a neutron star. And really, to be honest with you, what happens is it's such a large amount of mass that the gravity is so strong, it's actually compressing the matter inside the core to such a large extent that electrons are actually forced into the into the nucleus of the atoms that make up the star. And according to nuclear physics, that means these electrons are going to spontaneously turn the neutrons into the protons into neutrons, so that you literally get essentially a pile of neutrons that's spherical, and that's why they call it a neutron star. So it's literally a star that has the density of a nucleus, which is really high. For instance, a single tablespoon of this might weigh as much as a fully loaded Mack truck. So, anyways, that's the process. What we have here is solution. And for the solution, we need L1 is equal to L2. That's the conservation of angular momentum, which is satisfied here because there's no real forces acting on the star. It's rotating, but it's rotating in essentially a vacuum, so there's really no appreciable force on it. So since the net torque is zero on the system, which is the whole star, then the angular momentum dl/dt is equal to zero. The derivative of the angular momentum is equal to zero, and that means the angular momentum must be a constant. Now, that also tells us that the angular momentum is equal to I1 omega 1 is equal to I2 omega 2, and for a sphere, I is equal to 2/5 m r squared. So that's just something you know after you've memorized, after you've derived the formula for angular momentum, or excuse me, for moment of inertia a couple times. And of course, in your test, you'll actually have a table of moments of inertia for different shapes, so you wouldn't even have to derive it unless I ask you that as one of the problems. So this should be what we need to do. So I'm going to go ahead and start off by writing the left-hand side, which will be 2/5, and then the mass, which is two solar masses. So I'll just call that, we'll just call that big M. Even though it's two solar masses, what you're going to see is it's going to actually, the masses will cancel out on both sides, so that doesn't matter. And the initial radius is, oops, I'm writing it in the wrong area. No wonder. All right, let me copy this over to the screen above. Cut, paste. Okay, so yeah, I wrote it in blue. We'll get over that. That's not a problem. So 2/5 m times r1 squared times omega 1. And then after the collapse into a neutron star, it's still going to be 2/5. It's still going to have the same mass, but now it's going to have the radius r2 squared, and it's going to have the new angular velocity omega 2. So we can see right now that the 2/5 is going to cancel out with the 2/5, and the mass is going to cancel out with the mass. And that actually can give us that the omega 2 is actually going to be equal to R1 over R2 squared times omega 1. So omega 2 is equal to 7 times 10 to the fifth kilometers over 10 kilometers squared. And here's the part that's a little bit difficult. Just we don't normally want to talk about, especially when something's rotating this fast, we don't want to talk about revolutions per day, which is what we're given. So I'm going to convert it to revolutions per second, and therefore omega 1 is going to become 1.0 revolutions per 100 days times 1 day is equal to 24 hours times 1 hour is equal to 3,600 seconds, like that. And that actually reduces to, now you can see the day cancels out with the day, the hour cancels out with the hour, and you're left with revolutions per second, which is a much more usual and reasonable value. So if I take 10 or 7 times 10 to the fifth and I divide that by 10, I'm obviously going to get 7 times 10 to the fourth, and then I square that, and then I multiply that by uh, 1, and then divide that by parentheses 100 times 24 times 3,600. All of that's in the denominator, so I put parentheses around it. So I literally wrote 7 times 10 to the fourth squared times 1 divided by parentheses 100 times 24 times 3,600. And this gives me 567, which is one extra sig fig than we're entitled to, but that's 567 revolutions per second is equal to omega 2. So again, this is much, much faster, almost 600 revolutions in a single second, where it was only making one revolution in 100 days before. So that's a neutron star and a typical example of what happens when we have found these. In fact, when we first found them, if I remember correctly, this was the one where someone wrote down LGM because it was a signal that kept coming with such regularity that they thought that only a intelligence could create a signal like this because it was, if you take 1 divided by 567, you get 1.7 times 10 to the negative third second. So imagine you get a spike at 1.7 times 10 to the negative third second, another one at exact same time, another one at exact same time, another one at exact same time. It literally takes a long period of time before any kind of frictional effects causes it to slow down or anything. So they were seeing this really rapidly firing series of signals that were all equidistant in time, and it made them think, oh man, this might be a signal from an alien source. But it turned out to be something much more mundane, even though it was very exciting because it was a neutron star, which is a state of star matter that we had predicted but didn't necessarily know whether or not it worked or would actually exist. All right, so that's it. That's the velocity of this, or that's the angular velocity of this. And actually, let me make sure I answered everything. It said if it were to undergo gravitational collapse to a neutron star of radius 10 kilometers, what would its rotation frequency be? Now that's actually omega, and frequency they usually will use something along the lines of cycles per second, and that's really what I did by making it revolutions per second. I was really doing f. So you could actually have said all of these include a 2 pi f. So we might have actually called this omega, even though it really doesn't matter too much. We could have said omega is equal to 2 pi f, and then f is more likely seen to be in cycles per second, or what we call hertz. But a cycle and a revolution are pretty much the same, but they're also related to radians. So if it's in radians, that's definitely what we call omega. But if it's in cycles per second or revolutions per second, it could technically be f. But as you can tell, if I wanted to replace the omega 2 with 2 pi f 2 and the omega 1 with 2 pi f1, then we would still get the same thing because the 2 pi's would cancel out on both sides. So that's why it's perfectly fine to do it this way. Any questions on that? Again, no one's here, so I'm going to move on. All right, so we got that, and your book is calling this answer 6 times 10 to the 2 revolution per second, which is 600. And to be honest with you, they did call the radius 7 times 10 to the fifth, so it really should be 1 sig fig. And I guess if I'm going to be consistent with that, I should probably put an underscore under the 6 as well. So that'd be 6 times 10 to the 2. Now I'm going to move on to example 11.4, which is a neat one. It says running on a circular platform. Suppose a 60 kilogram person stands at the edge of a 6 meter diameter circular platform, which is mounted on frictionless bearings and has a moment of inertia of 1800 kilogram meter squared. The platform is at rest initially, but when the person begins running at a speed of 4.2 meters per second with respect to the Earth around its edge, the platform begins to rotate in the opposite direction as in figure 11.5. Calculate the angular velocity of the platform. So let me show you a drawing of this. Actually, I'll show you two drawings. So there's the disk, and then I'll make a copy of this disk just to save myself the hassle of drawing it again. Oops, that was not quite as time serving as I'd hoped. I hit the wrong button. So there's the disk in one instant, and in one instant, what we have here is a person just standing still like this. But in the next instant, what we have is the person running, and that person is in fact running at a rate of 4.2 meters per second or relative to the Earth. And of course, he would, in principle, be moving in what we would consider, if we're looking from above, what we would consider to be a counterclockwise direction. And because of that, that's going to cause the actual disk via conservation of angular momentum, it's going to rotate in the clockwise direction. So when this happens, that means the disk is going to rotate this way with a angular velocity omega. And what we're asked to compute here, of course, is calculate the angular velocity of the platform. They want to know what omega is. Not I wrote VD for the velocity of the disk, but they really wanted the omega D. So to make that consistent, I'll put this omega D right there. All right, so that's what we're shooting for. And of course, the solution requires us to write I1 omega 1 equals I2 omega 2. And we also are required to say the moment of inertia is 1/2 mr squared for this disk, but we don't really need that because they gave us the actual value. So we don't even need the 1/2 mr squared value because they didn't give us mass. All they really gave us was the angular or the moment of inertia and the actual mass of the person. But we are required to figure out the moment of inertia of the person, and we're going to treat them like a point particle, and therefore it's just mr squared, where r is the actual radius of the disk. So I can now say I1, this is the initial state that I drew on the left, so initial and final. And I initial is, or excuse me, I omega initial is equal to I omega final, like that. And with that, we can say that 0 is equal to, because neither the disk or the person is moving, so the angular momentum initially is 0. But after this, we get a moment of inertia for the person, which is going to be mr squared times, in this case, it's going to be mr squared times omega, but omega is v over r. So we're going to say mr squared times v over r, and that's for the person, plus I for the disk times omega for the disk, like that. And your book actually chose to put this as one being positive and the other being negative. I like to put them both as positive so that we can see that when I put in a positive velocity for the person, we'll get a negative angular velocity for the disk. So it'll show us definitively that the two angular velocities are actually in opposite direction, which is what conservation of angular momentum would require. So from this, I can say 0 is equal to 60 kilograms times the radius of the disk, which is 3.0 meters. That'll be squared. And then we're going to multiply that by the 4.2 meters per second divided by the 3.0 meters as well there. And then that is equal to the 1800 kilograms meters squared times omega disk, like that. And from this, we can get omega disk is equal to a negative, of course. I'm going to say 6 times. Now, notice I got 3 squared, but the 3 squared is going to cancel out the exponent of 2 with the number on the bottom. So I'm just multiplying 6 times 3 times 4.2, and that gives me 75.6. Oops, meant to keep that in blue. So that gives me 75.6 kilograms meters squared per second is the angular momentum uh, of the person, and we called that one positive. And then that's going to be divided by the 1800 kilograms meters squared, which is the moment of inertia of the disk, and we get 75.6 divided by 1800. That gives me 0.042 revolution, or in this case, it's going to be, oh, I should put a negative there too. Don't let me forget the negative. That was the whole reason I put the plus in there, was so that I'd get the negative out. So this is going to be 75.6 divided by 1800. Let me make sure that was 75.6. 60 times 3 times 4.2. Oh, I typed in 6. No wonder. This is not 75.6. This is 756. Sorry about that. When I typed in the 6, I typed in a 6 instead of 65, or instead of 60. So this is 756. And then that 756 is going to be divided by 1800. And therefore, we get negative 75 point, or 756 divided by 1800 gives me 0.42 radians. Notice the units actually just come out in reciprocal seconds, but we can add that radian in. So that's going to be the omega, the angular velocity of the disk is going to be negative 0.42. And again, that just means that it's going in the opposite direction as the person runs. So the person's running in a what we consider a counterclockwise direction. The disk is going to rotate in a clockwise direction, and that velocity is markedly smaller because obviously the moment of inertia of the person running at the edge, even though they're 60 kilograms, and even though they're at the edge, that's as big as it could be given that mass. It's still not a very big comparison to the 1800. So the 1800 makes the velocity much smaller. In fact, it's more or less a factor of 10 less. Any question on that? Actually, it's exactly a factor of 10 less. But anyways, all right. This brings us to conceptual example 11.5, and I normally don't draw these, but this one's one that I really should. So, conceptual example. I normally don't write them. I normally don't write them, not necessarily don't draw them, but I normally don't write them or anything. I just explain them verbally, but this one really needs some pictures. So this is conceptual example 11.5. And it says spinning bicycle wheel. Your physics teacher is holding a spinning bicycle wheel while he stands on a stationary frictionless turntable. What will happen if the teacher suddenly flips the bicycle wheel over so that it is spinning in the opposite direction? So what we'll do is as physics teachers, we often buy these as a demo anyways, but you could just take a regular bicycle wheel and then put some kind of attachment on the ends of the actual axles, the screw ends that come out of the hubs. We'd put a little screw knob or something like that so we'd have a handle, and then put another handle on the other side so we could actually hold it, and it would also not unthread from the axle and cause an injury or anything. But other than that, it's basically just a bicycle wheel. And then we get the bicycle wheel turning really fast, and then we'd say hold it like this so that it's spinning, say, this way. But what they're saying here is you're going to hold it like this while you're standing on a turntable, and then turn it upside down. And they want to know what happens in that case. So let me show you that. I'll go ahead and draw a figure so you'll have some understanding of what we're talking about. But this is the disc you can imagine the instructor standing on. He's going to stand roughly over the center for best results. So we'll say he stands like this, and then we'll say his shoulders are actually at some angle like this so that this arm can hold the bottom part of the wheel, and then the other arm can be used to hold the other part of the wheel. And with that, he's going to have the wheel spinning. Ooh, I didn't really draw that very centered up, did I? So he's going to have the wheel spinning like this, and we're going to say the wheel is initially spinning this direction. So with that, we're going to say what happens when he turns it the other way. So right now we have, and I've discussed this before, but basically if the disk is rotating this way, which looks like counterclockwise when looking from above, then you curl your fingers in the direction that it's turning, and this is your fingers of your right hand, and your thumb then points in the direction of the angular momentum. So what that means is this initial angular momentum L1 is actually up. So that's the direction of L1. And then after he changes it, we're going to have the same person, of course, standing there, the same cattywampus shoulders and stuff like this, only now he's got it sort of turned the opposite way. So I'm going to tilt my shoulders or tilt the instructor's shoulders differently. And now this arm is going to be on top and the other arm is going to be on the bottom so that we have something like this. And now the wheel, oops, now the wheel is going to rotate in the opposite direction which means like that. And that means the moment of inertia, or excuse me, the angular momentum here is L2, but they're supposed to be equal in magnitude, even though they don't look like it from my diagram. I can make it look a little better by doing that. So that's what's going to happen. And they specifically said what will happen if the teacher suddenly flips a bicycle wheel over. Well, what's going to happen is the angular momentum initially, Li, is just L1. And actually, I'll just call that just plain L. And the reason why I'm going to do that is because the L, if I call one L1 and the other one L2, that could imply that the two have different moments of inertia, or excuse me, different magnitudes. But if I call them both L and have them drawn next to vectors pointing in the opposite directions, then it's obvious they have opposite directions but equal magnitude. So that's what I'm going to do. So L initial for the whole system. And by the way, the system is the instructor plus the turntable plus the bicycle wheel. And in the initial scene, you only have the bicycle wheel turning. So the only angular momentum is the angular momentum of the bicycle wheel. But after he turns it upside down, conservation of momentum is going to dictate that the total angular momentum must be L1 again, or excuse me, L again. So now I'm going to say L final, and I should stick to purple, I guess. L final still has to be equal to L, but in this case, it's going to be L down, which is minus L, plus the L for the disk and instructor. So I'm going to say LDI for disk and instructor. Now, we can say conservation of momentum. Conservation of momentum is factual at this point because we're assuming everything's frictionless and the system is such that yes, the instructor put a force and torque and stuff on the wheel, but the wheel and the instructor and the disc itself, all of those are part of the system. So any force between the disc and the person, between the person and the tire, or between the tire and the disc, all of that wouldn't matter. So that all we have is the forces from outside. And if we assume this turntable is nearly frictionless, then we're not going to have any net torque. Since the net torque is zero, that means dLdt is equal to zero. And since dLdt is equal to zero, that means L is a constant. And that's what we mean when we say conservation of angular momentum. So now conservation of angular momentum dictates that L is equal to negative L plus LDI. Now remember, we're all talking about angular momentum that just points up or points down. So it's still a vector quantity, but the vectorness of it is indicated by the plus or minus. So the fact that L in one case is negative means it points down. In the case of the other case where it's positive, it points up. But we can now solve this for LDI, and we see that LDI, of course, is going to be equal to 2L. So, in fact, in order for this instructor to take the wheel and turn it upside down like this, now him and the disc are separately going to have or together, are going to have a total angular momentum twice as big as the angular momentum the wheel had. But remember, he's really, really heavy, and probably the turntable is kind of heavy, so he's not going to rotate very fast, but he will rotate, and that means he's going to rotate in the opposite direction, or excuse me, the original direction, whereas the wheel is actually rotating in the opposite direction now. So the result is the instructor and, oops, and the turntable, yeah, the instructor and the turntable will now rotate in the direction that the bicycle wheel originally turned. Oops. That was a really rough looking R, so I've made it bigger. Originally turned and their total L will be twice the L of the wheel. And that's what happens. So, yeah, they're going to have a net angular momentum that's twice as large of the angular momentum that the bicycle wheel have, because the bicycle wheel is doing one of those units of angular momentum down. And when you add that with two of those units up, two minus one gives you one. So you're back to where you started from. And that's what's going to happen. So that's conservation of angular momentum as demonstrated by a professor standing on a turntable holding a bicycle wheel. No one's here, so I'll move along. We already talked about the vector as a cross product. We've already done some examples. Actually, I think with your class, I have it right here. Let me double check. Did I do an angular momentum calculation with the cross product? I didn't there, but I thought I did in the previous one. So, anyways, let's just do that. I'll go ahead and do an example of the cross product. And I just want to remind you, with the cross product, they give you a lot of additional rules. A cross B is equal to the negative of B cross A. A cross A is zero. Some of that comes from the fact that the magnitude of A cross B is A times B times the sine of theta. And of course, if the A and if you're taking a cross product of A with itself, then they are in fact two parallel vectors. So the theta between the two vectors is zero, and the sine of zero is zero. So that's why you get that. But they do have an example on here, and I'm just going to work that real quick. The torque vector. And they said specifically example 11.6. So here we go. So example 11.6, they're saying R, the lever arm vector, is equal to 1.2 meters I hat plus 1.2 meters. Oops. Yeah, 1.2 meters K hat. Notice that's not I hat and J hat. That's I hat and K hat. And then they said the suppose the vector R is in the XY plane is in figure 11 and is given by R equals 1.2 meters I hat plus 1.2 meters K hat. Calculate the torque vector tau if F is, so here's the F. The F is going to be 150 newtons in the I hat direction. And they want us to calculate torque equals question mark. So solution, I want to go ahead and mention some of the things I said. Torque is equal to R cross F. It's always the lever arm crossed with the force, so that's part of it. And we always know that that is the determinant of a 3 by 3 matrix, the first row of which is I hat, J hat, K hat, the second row of which is RX, RY, RZ, and the third row of which is FX, FY, FZ. And we also know that the magnitude of the torque is equal to R times F times the sine of the angle between them. So if you put them tail to tail like this, then this would be the angle theta. And of course, R cross F in this case would be mutually perpendicular to both of them. So that's a right angle there, and it's a right angle there. This would be the torque vector. So that gives you some information about the cross product. So let's go ahead and calculate this torque. So torque is equal to the determinant of this matrix, which we said was I hat, J hat, K hat. Then we had 1.2. I'm going to leave the unit off. 0, 1.2. And then we had 0, 0, 150. Again, leaving the unit off. So I first expand upon the I hat. So I write the I hat out in front, and then that's the one, the I hat and the K hat do the normal number. I don't have to multiply it by -1, in other words, because it's -1 to the 1 plus 1 power, which is the 2 power, and -1 to the 2 power is 1. So in this case, I imagine hiding this column and this row, and I just get left these four elements down here, and the normal determinant is this times this minus this times this. So we see this is going to be, let me put a square bracket around it so I can show exactly what I'm doing. It's 0 times 150 minus 1.2 times 0. You can see you're not going to get anything from that. Then I can do J hat. Now this is the one we have to do backwards. So when I cover up the J hat, that gets rid of that column and that row. So it leaves these two as the left column of a 2 by 2 and these two as the right column of a 2 by 2. And because this is the one that has the -1, I just do it in the opposite order. So I say this times this minus this times this, ignoring that 0, 0 column. So with that in mind, what I get is 1.2 times 0 minus 1.2 times 150. And then finally, plus k hat. Now this time we're going to cover up this column and this row, and we're just left with this 2 by 2. So I'm going to say this minus this. And in this case, we get square bracket 1.2 times 0 minus 0 times 0, like that. And that basically just gives us a total of 0 for the I hat component, a total of 0 for the K hat component, but we will get a J hat component, and that's going to be negative 1.2 times 150. 1/10 of 150 is 15, so 2/10 is 30. So this is going to be negative 180 Newton meters in the J hat direction is equal to the torque, and that's the result. So hopefully that works out. Mm, wait a second here. Let me look at my J hat again. Your book said that was a positive. Oh, did I misread? I think I misread my F. Yep, yep. I put my F in the K hat direction instead of in the I hat direction, and I actually wrote it right. So I tell you what, to make these notes right, I'm going to say this is an altered example. 11.6, and the alteration I'm making is I'm putting this as K hat. You can see the difference would be because I put the 150 there. Sorry about that. I swore I'd remembered it being in the Z direction for some reason, but it was wrong. I clearly wrote it down as the I direction. So this is the right answer if the force is in the K hat direction. If the force is in the I hat direction, then the answer would have been 180 Newton meters in the J hat direction as well. It still would have been the J hat, but it would have been a positive. So hopefully y'all could actually maybe plot these to the radius, the lever arm vector, and the force vector in the two different cases, the example 11.6 as well as the altered example 11.6, and hopefully that'll convince you that they should be in fact opposite in sign. So I apologize for that. I recorded correctly, but put F component in wrong slot. So it should have been Okay, but the way I worked it, everything I did was right except for putting it in the wrong spot. So it still came out with a correct answer for the other problem where F is equal to 150 newtons in the K hat direction as opposed to the I hat direction. All right, that's what happens when you decided on the fly to do a problem that you hadn't prepared to do. So I just wasn't paying attention and screwed up. All right, now we're going on to angular momentum, and this is where we're going to talk a little bit more about particles, and I'm going to cover example 11.7. It says a particle's angular momentum, and actually this one I discovered I still need to write it down, so I'm going to say conceptual example 11.7. I remember when I covered this last time, I was probably spooked some students, so it's probably be a little bit better if I instead go ahead and explain what I'm doing. It says a particle's angular momentum. What is the angular momentum of a particle of mass m moving with speed v in a circle of radius r in a counterclockwise direction? So one of the angular momentums that I told you about was L is not only I omega, but also L can be R cross P, where P is equal to mv. Because of that, you can say L is equal to R cross mv like that. So if we're talking about an object going in a circle like that, then we might imagine the middle of the circle is right about here. We could say the R vector, which points from the center of rotation to the point of the actual particle, would be that R vector. This would be the mass right here, and the velocity of that mass, if it's going, for instance, in a counterclockwise direction, the velocity would be that way. And notice, because it's tangential to the circle, this vector and this vector are perpendicular to each other, even though my drawing is not so certain on that claim. It doesn't look perfectly perpendicular, but maybe I made it a little better there. So when we go to cross product them, what we get is L is equal to, since they're perpendicular, we know the magnitude is equal to R times M times V times the sine of the angle between them. But the angle between them, of course, is 90 degrees, so we get R times M times V times the sine of 90 degrees. And the sine of 90 degrees, of course, is 1. So we're going to write this as m times v times r. It feels more natural to write it that way, but it's really misleading because it makes you think that the momentum crossed with the r is the angular momentum, but it really should be r crossed with the p is the angular momentum. Now, that's what we know is the angular momentum, but we also know that L is equal to I omega. So if we look at this as I omega, then we could say, all right, L equals mvr is equal to I omega, and we use the fact that V is equal to R times omega, then we could say that V should be R times omega, and that would give us instead m R omega times R is equal to I omega. But we could also rewrite this so that it looks like I times omega. And when we did that, we'd get m r squared times omega equals I omega. And that's really what we're shooting for, is we wanted you to see what I claimed earlier, which is the moment of inertia of a point particle going around in a circle is just mr squared. So that's one of the things we discovered. So we now have L is equal to I omega, and I is equal to mr squared for this scenario. So that's really what the conceptual example was about. Now we'll press on angular momentum and torque for a system of particles in general. Now this is where they're expanding it, because it turns out you can use that summation of the torques is equal to I times alpha, or summation of the torques is equal to dl dt. You can use that for a rigid body as if the rigid body is made up of a sum of a bunch of individual parts because really in reality all matter is made up of atoms, so there's a finite number of atoms, albeit a really big number. There's a finite number of atoms, and if the body's rigid, that just means the distance between any two particles is never going to change. And additionally, if you drew a line between two particles, like from this particle to this particle, and then you drew a line from one of those particles to another particle, then that angle between this line and this line is always going to stay the same as well. That's really what a rigid body is. And you can work this out, and this is what your author's doing, and you'll find out that if you calculate the angular momentum, or excuse me, if you try to calculate Newton's second law for that system of, a very large number of atoms and of a rigid body, you still get the summation of the torques is equal to I times alpha, or the summation of the torques is equal to dl dt. And it turns out, even if it's not a rigid body, you can still get the same result. We can even apply it, for instance, to a flock of birds, for instance. But that's what your book is talking about. A flock of birds is a little bit more difficult because they have their own brain and they can move in different ways. They're not necessarily beholden. They're beholden to the laws of physics, but they can also apply forces to themselves that make it a little bit different. And the force to itself could actually be caused by the air outside of the system, which is not part of the system, and therefore it's very easy to run into a case where you think it's conservation of angular momentum is true, but it's not because there's a force acting specifically on one of the geese or one of the birds in such a way that it's not. So anyways, let's go on now and I'll show you how to use this. Your book actually does the derivation of all this. I highly recommend you reading it so you can better understand it. As you go on, and especially if you're going into engineering, you're going to have a statics class and you're going to have a dynamics class. When you get to dynamics, the more you understand about these derivations, the better off you'll be in dynamics. Or if you become a physics major, then you're going to have a course in mechanics, and that has kinematics and dynamics as well. And the more you understand about this derivation, the better you'll be. And in general, anybody that understands the laws of physics at a level where they can repeat or even just understand a derivation are much better off by understanding that derivation or by even being able to complete it. So now that we've talked about that, I'll use the actual equations we learn. But your book talks about angular momentum and torque for a rigid object, and that's what I was just talking about. So I'm going to now apply this equation that we derived for a specific example, and the example is example 11.8. So let me separate this from the other example. So we're going to say example 11.8. This is Atwood's machine. An Atwood machine consists of two masses, MA and MB, which are connected by an elastic cord of negligible mass that passes over a pulley. If the pulley has radius r0 and moment of inertia I about its axle, determine the acceleration of the masses MA and MB and compare the situation where the moment of inertia of the pulley is ignored. Ignore friction at the axle O. Okay, so what we're given here is a radius R0. Sorry about that. We're given a radius R0 for the pulley. We're given, in principle, we could be given a mass for the pulley, but we're not necessarily given that, so I'm not going to write it. But we are given a mass M sub A and a mass M sub B for the two masses hanging on the pulley. We are given that the moment of inertia for the pulley is I. That replaces the mass, of course, and the drawing for the actual diagram for the figure for the problem is this. You have a pulley like that, and you have a radius R0, and of course it's R0 on this side. And the reason why we're drawing them here, and this is the origin or the rotation axis right there where that O is, the reason why we drew them there is so that you see that the lever arm is actually going to be perpendicular to the tension that's caused by the cords. So we're also going to go ahead and draw the cord going down this way and this cord going down this way, and this mass, oops, this mass is going to be M sub A, and this mass is going to be m sub b, like that. And what we're going to imagine is that the MB is maybe heavier, so that's going to cause the pulley to rotate this way. That's going to cause the MB to go down that way and the MA to go that way. In order to do this, like if we're using Newton's second laws and stuff, we would want to actually take the time to make sure that the positive acceleration on the left is in the same direction as the positive angular acceleration of the pulley, and that's the same direction as the positive acceleration downward on the right. So, in other words, we would say the positive y-axis on the left-hand mass MA is up. The positive rotation and therefore positive torque is clockwise, and then the positive y-axis points down on the right-hand side. By doing that, you don't have to use weird things like v is equal to negative r omega or a is equal to negative r alpha, that sort of thing. Now, whereas again, as I said, we're assuming the acceleration is up that way and is down that way. And by the mass or by the string being not stretchable and by being basically having no mass, the fact that as this thing rolls out, more and more mass of the string is going to be on the right hand side. And in principle, even if it's a very low mass, it could in principle add up to be a large mass. But we're saying that mass is zero, so we don't have to take that into consideration at all. And the fact that the string doesn't actually stretch means that if the particle on the left or the box on the left moves up 1 inch, the particle or the box on the right moves down 1 inch. If it moves up 1 inch in 1 second, the one on the right moves down 1 inch in 1 second. If it moves up 1 inch in the first second and up 2 inches in the second, the right's going to move down 1 inch in the first second and down 2 inches in the second. That convinces us that V is equal to R times or that V of A is equal to V of B in magnitude, and it convinces us that the distance traveled by A is equal to the distance traveled by B, and it convinces us in the last part that the acceleration of A was the same in magnitude as the acceleration of B. Now, in addition to that, we're assuming the pulley doesn't actually have the rope slip along it, so if when the mass MA went up 1 inch, we would expect that the last part of the rope or the first part of the rope touching the pulley would change by 1 inch as well. So that locks them all together so that they're all related by A equals R times alpha, V equals R omega, S equals R times theta, that sort of thing. So now, how are we going to go about solving for this? We're supposed to determine the what was it? Determine the acceleration, if I remember. Yeah, determine the acceleration of the masses MA and MB. So what we're going to use here is solution. Oops, I meant to write that in purple. Solution. We're going to do it a weird way compared to what you've been doing so far. We're going to actually use torque equals dl dt, and that is actually a vector equation. But notice all the rotation and the v's and the stuff, they're all the accelerations in linear are one dimensional. The rotation is actually, two dimensional, but the vector representing it either points out of the board or into the board. So that's all one dimensional. So I'm just going to drop the vector symbols and say torque is equal to dl dt. And technically it's the sum of the torque, so I really should write it that way. That being said, let's go ahead and calculate what the angular momentum is given the fact that the acceleration is a, which at any split second would give a particular velocity v or something like that. So with that in mind, we're going to say L is equal to, it's the L is going to be the angular momentum of the mass uh, which is headed towards the pulley. And remember, L is equal to R cross P, and R cross P means R perpendicular to P times P, or it means P perpendicular to R times R. Or you could say R times P times the sine of the angle between them. The big thing is, because of this, the actual angular momentum of MA is just going to be MA times velocity times R0, just like we saw in the previous problem. So this is going to be MA. Oh man, it jumped to drawing my stuff again. So it's going to be MA times V, because at any split second we might say, and I'll draw this in a different color. I'll say this is A, or excuse me, this is V. like that, and then this one would be v. So that's at a split second in time are those velocities, but the acceleration is what we're really trying to calculate. So ma times v times r0 is going to be the actual angular momentum for v for the mass ma. And then for the mass MB, that's going the same direction. They're all tending to rotate the disc this way or the pulley this way. So that means they're all a comparable angular momentum. They all have the same sign. So this one's going to be MB times V times R0. And then we have the moment of inertia for the actual pulley. And that moment, or excuse me, the angular momentum for the actual pulley. And the angular momentum for the actual pulley is I times omega. So that's going to be I times omega for the pulley. But again, we're going to say V is equal to R omega. So omega can be replaced by V over R. So with that in mind, I'm now going to find out that we have a common factor of VR0. So I'm going to write this instead as MA plus MB times V times R0. And I know that R is leg is not really horizontal, but I made it look that way. And then we're going to say plus. Now, in this case, this is where we're using V equals R omega. The fact that the rope's not sliding on the pulley tells us that the linkage between the omega and the V is omega is equal to V over R. So in this case, I'm going to say I times V over R0. That's the total angular momentum. Now, what are the torques? So the summation of the torques, and I'm treating uh, a clockwise rotation in this case, I'm treating that as positive so that the MB times G pointing down is a positive torque. So in fact, it's going to be MG times MB times G is the force, and then that's multiplied by the R0 to get the torque. So this is going to be M B, G, that's the force, and that force is perpendicular to the lever arm, and the lever arm has a magnitude of R0. And then in addition to that, we have the other pulley, the other mass on the other side, that's actually slowing down the ability of the pulley to rotate this way. So that's actually in the negative direction, and that's going to be MA times G times R0. So that's our net torque, if you will. Now we know that the summation of the torques is equal to dl dt. Therefore, we can say the summation of the torques is equal to d by dt of ma plus mb times v times r0 plus I times v over r0. So we're going to take the derivative of all that. Uh, the masses are not changing, the radiuses are not changing, the moment of inertia is not changing. The only thing that's really changing is the velocity. So we're going to get ma plus mb in parentheses times r0 times dv dt plus I over R0 times dv dt, and you see that that all can be reduced to ma plus mb parentheses R0 plus I over R0. All that will be multiplied by dv dt, but dv dt is equal to A. So we can now figure out exactly what A is by solving for A. What we have to do is put the summation of the torques on the left. So that's oops, that's going to be, I'll factor out the common factor of R0 and G. So we're going to say summation of torques is equal to dl dt. Therefore, we're gonna get MA, or excuse me, MB, and I used a lowercase m, so I should do it again. MB minus MA times G times R0. That's the summation of the torques part. That's equal to the other part that we just found, which is that big MA. Actually, I don't want to write it here. Let's do this. I'm going to move this down, cut, paste. So I'm going to move it right here so I have a little bit of room. So that's the left-hand side. The right-hand side is going to be square bracket times parenthesis MA plus MB, close parenthesis times R0 plus I over R0 times A, so that now we see A is going to be equal to MB minus MA over MA plus MB, oops, times R0 plus I over R0 like that. And then, of course, we still have a factor of R0 up top and a factor of G, which I'm going to put over here. Now, in this case, it would actually be better for us to multiply by 1 over R0 by 1 over R0 on top and bottom. So I'm going to go ahead and multiply by 1 over R0 on the top and 1 over R0 on the bottom. That's multiplying by 1, so we're perfectly allowed to do that, or we're perfectly justified. And in doing that, I get MB minus MA over MA plus MB plus, now in this case, notice the R0 on the top disappeared. The R0 next to the MB plus MA disappeared, but the R0 under the I became R0 squared, so it's over R0 squared like that. And then all of this is times G. And that is the actual acceleration. And you can see if I goes to 0, then A is equal to MB minus MA over MA plus MB times G, which is the same thing that we got before for the Atwood machine. So that's it in its entirety. That finishes example 11.8. And now we can move along to another example. This one's really nice. This is example 11.9, and it's another conceptual example, but again, I think it's a one that I need to write down the stuff for. So conceptual example 11.9. Now I'm going to draw a little hand. So here's the arm coming down. There's the wrist, and then you have a, ooh, that was a fat hand I had drawn there. So there's your first, your pinky knuckle, then your ring finger knuckle, then your middle finger knuckle, and then your index finger knuckle. And that tells me my arm's going to be a little bit too thin with that scenario. And then I'm going to picture my thumb as going like this. So there's the actual arm and the hand and the wrist. Now in this is in fact the end of one of those bicycle wheels that we drew in the previous example. So here's the actual axle, if you will. And then, or this is the handle on the axle. And then we have, actually, let me do this with the nice drawing tool. Like that. So that's really going to represent our bicycle wheel. And here's the end of that handle that's in the hand. And then, of course, here's the hub of the bicycle wheel. And then there'd be another handle in principle right here. And I want to try to make it comparable to the other side. So I'm going to say it looks like that. Now, the spokes, of course, are going this way and that, and the tire is actually going to be imagined to be rotating this way. Okay, so that's the way the tire is rotating, and therefore, by the right hand rule that we use to determine the direction of angular momentum vectors and angular velocity vectors, would tell us that this is the angular momentum of the actual wheel right now. Now, what's going to happen is I'm going to go ahead and draw a X, Y, Z axis. So here's my Z axis pointing up. Here's my y-axis pointing to the right. Both the z and y-axes are in the page, laying on the page, in other words, and the x-axis is pointing out of the page. So the x-axis is pointing out towards us, but we draw it at that 45-degree looking angle so that we can see that it's 3 dimensions represented by 2 dimensions. So there's our bicycle wheel. And what they ask us for is the following. Suppose you're holding a bicycle wheel by a handle connected to its axle, as in figure 1117A, which I've drawn here. The wheel is spinning so that its angular momentum L points horizontally along the y-axis as shown. Now you suddenly try to tilt the axle upward, and it says along the z-axis. I'm not sure people follow that, so I would normally say now now you suddenly try to tilt the axle upward by rotating your wrist about the x-axis. So the x-axis is like an axle you could imagine going right through your wrist, and we're trying to imagine holding it initially. Let me show you this way. Initially, we're trying to hold it like this, and we're trying to lift up like that with the x-axis going through it. So it's really a rotation about the x-axis is what we're trying to accomplish. So what we're imagining here is the hand goes from this position. I should draw this in green. It goes from this position, 1, 2, 3, 4. Whoa, that was nice how it just automatically changed my drawing, wasn't it? 1, 2, 3, 4, and like this. There's the thumb and going like this. And what we're imagining is it's going to rotate this way. Notice that's a rotation about the x-axis, and that's going to make the hand go down like this instead. 1, 2, 3, 4. Like that. So that black is supposed to be the hand after I've tried to rotate it, even though I can't really rotate it that way, as you're going to see. So that's what's going on here. It says, suppose you're holding a bicycle wheel by a handle connected to its axle, as in figure 1117A. The wheel is spinning so that its angular momentum L points horizontally along the y-axis as shown. Now suddenly you try to tilt the axle upward along the z-axis so the center of mass moves vertically, or also so you can imagine the your wrist twisting by some counterclockwise angle about the x-axis. You expect the wheel to go up, and it would if it weren't rotating, but it unexpectedly swerves to the right. Explain. Take the system as the wheel, axle, and handle. Your hand is external. Okay, so what we see is currently the angular momentum is pointing to the right. And what we're trying to do is apply a torque, which is in the counterclockwise direction about the x-axis. So torque is this way, which that's the rotation, and that means the actual torque vector is that way. Okay. Now, the whole reason I'm saying that is the following. The summation of the torques is supposed to equal dl dt, which we can say approximately the summation, actually, I'll just say it like this. The summation of the torques is approximately delta L over delta T. And really, the only torque we're talking about here is just the torque that the hand is applying to it. So I don't need to continue writing it as a sum of the torques. I can just say a single torque. So I'm now going to say torque hand is approximately equal to delta L over delta T, and that means delta L, which equals L final minus L initial. Delta L is equal to the torque from the hand times delta t. So that's what delta L is. Now, delta L, like I said, is L final minus L initial, but it's also equal to tau times delta t. Well, tau is the vector that points along the x-axis. So if I drew another xyz axis, this is what happens. Here's your y-axis. Here's your z-axis. Here's your x-axis. We have the initial angular momentum vector is L initial. And then we add to that. Notice I'm trying to draw this parallel to the x-axis. We want to add to that the torque times delta t, because multiplying the torque times delta t actually gives us a vector that has the same units as L, so it can be added to L. And we're trying to think delta t is really, really small, but I needed you to see the actual change, so I drew it a little bigger than I would otherwise want to. And now what you see is the delta, or the final angular momentum, L, points from the origin to here. So this is L final that way, because specifically delta L is equal to L final minus L initial, which equals tau delta t. So L final is equal to L initial plus tau delta t, like that, or delta tau, like that. So by seeing the fact that the torque is coming out of the page, and when you multiply that by delta t, then it has the same units as L, so you can add that vector pointing out of the page to the vector that we already had, which is pointing to the right, and that gives us a vector instead pointing to the right on the paper. That gives us a vector instead that's pointing a little bit out of the page, but mostly to the right. So even though you tried to rotate it up by twisting your wrist about the x-axis in the up direction, what actually happened is the wheel turned to the right, which is what we were asked to explain, and that's what we just figured out. The purple vector is consistent with the wheel's axis turning to the right. Oh, Jesus. The purple L final vector, and really, since I put vectors there, I really should have put vector symbols on everything. So the purple vector, L final, points with, or let's say has, instead of points, I'm going to say the purple vector has a large y component like L initial, but it also has a positive x component, which suggests the attempt to rotate the wheel's center of mass upward resulted in the wheel's axle turning to its right. And that's really what we were asked to explain. So now we see what it was. Because we were doing a torque that was along the x-axis, if you multiply torque by a small delta t, you get a vector that can be added to the L, and it needs to be added to the L because it turns out the L final is the L initial plus t, plus tau times delta t, and tau times delta t points in the positive x direction. So when you add a vector with a y component only to a vector that only has an x component, then you have an x and y component, and the result is now a vector with both the x and y component. And that meant the actual angular momentum vector, which is parallel to the axle of the wheel, instead of moving up, sliding along the z-axis, it's actually going to slide to the right to some extent as a result of you trying to turn it up. That also, by the way, happens to be the reason that they teach you what they do if you take a motorcycle driving course. In the motorcycle driving course, which I highly recommend if any of you are planning on riding motorcycles, which I don't necessarily recommend because there's so many chances for bad things to happen. I've lost some friends this way, and it's just a terrible thing. But anyways, if you do, the best thing you can do is take the driving course, the motorcycle driver's course. They'll give you a discount on your insurance. They allow you to bypass taking the actual driven test for the motorcycle license as well. So there's good reasons. But additionally, they just teach you a lot of good stuff. And one of the things you're going to learn is going to flip you out if you didn't already know it. And they tell you specifically uh, if you want to turn right, you push the handlebar forward to the right. Now, think about that. If you're riding a bicycle and you want to turn right, you normally take the bicycle handlebars and turn them this way, and it goes to the right. But they're saying, and this is only true, it happens. Happens to actually occur at a sort of slightly higher than 5 or 6 mile per hour speed. If you're going faster than 5 or 6 miles per hour, then you should do it this way, like they teach in the class. Specifically, if you want to turn right, you're going to push the handlebar on the right side forward, and then that's going to make you turn to the right. It's weird, right? But I went out and tried it, and the same thing's happening here with the motorcycle. You initially have the two wheels uh, riding like this, and your motorcycle, for instance, is going forward. So here's your motorcycle, and here's your handlebars like that. And since the motorcycle is going forward, the angular momentum is this way. That's the L for the front, and that's the L for the back. That's your angular momentum vector. If you try to turn your handlebars by rotating this direction, that means the torque that you're applying is actually in the up direction. So when you go to try to make a torque in the up direction, if you imagine multiplying that by delta t, then you say torque is equal to delta L over delta T implies delta L is equal to torque times delta T, and that means L final minus L initial, and I have to write that because I used the F over there, is equal to torque times delta T, and that tells us that L final is equal to L initial plus torque times delta T. So you can see now that the angular momentum, which was purely pointing to the left, say, now has added to it the torque times delta T, and that means the final angular momentum L final is actually has not only a horizontal component, but now it has a vertical component as well. And what happens is the bike actually tilts when you push the front right hand side of the handlebars forward. The bike is going to tilt to the right, and when you're doing that, then the radius of the tires becomes smaller, and that makes you make a tighter circle, and therefore you turn to the right. But that's really the physics of why they tell you in a motorcycle driving course, if you want to turn right, you push forward to the right. So you push the right hand side forward. Or specifically the wording they said is if you want to turn right, push right. If you want to turn left, push left. And you can see that, like if you watch movies, old Chip episodes of Chips, you'll see police officers. Sometimes they have to lay their motorcycles down, and of course, there's stunt doubles doing it. But you'll notice that when they do it, they always will push that handlebar forward on the left-hand side, and that sets it in motion. Because to lay a motorcycle over without getting killed is not a trivial task. So you really need some trained drivers, and if they were thinking in terms of leaning as opposed to in terms of applying the torque to the handlebars in the right direction, then they're liable to bend too far or to lean too far over or not far enough and end up being in one of those situations where the brake hits the tire and it causes the motorcycle to roll and flip over or slings you, which all of which is really bad. So anyways, that finishes example 11.7. I highly, 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 highly recommend you reading the paragraphs after example 11.7 and the rotational imbalance and the diagram and the paragraph in between rotational imbalance and example 11.9. Read that as best you can, and then you'll make some sense. Hopefully, if you understand it well enough, you'll be able to make some sense of how balancing tires works on your car. Let's look at torque on an unbalanced system. I'm going to skip the torque on an unbalanced system. That's example 11.10. That's a pretty neat problem, and it actually goes with that, but it's a little more advanced, a little more complicated to follow than I'd normally like to cover in class, and I'm certainly not going to test you on it. So we're going to move on to the next subsection, which is conservation of angular momentum, which we've already been doing, but we're going to do example 11.11 now. So let's look at example 11.11. Now, we only have about 30 minutes left, so that's okay. Kepler's second law derived. Kepler's second law states that each planet moves so that a line from the sun to the planet sweeps out equal areas in equal times. Use conservation of angular momentum to show this. So what I'm going to do is I'm going to draw an ellipse because we learned in chapter 6 that Kepler's first law is that the planets orbit the sun in elliptical orbits with the sun at one focal point. So I'm going to draw that right quick, and there's sort of our orbit. I'm going to say that's our sun right there. And now I'm going to imagine a planet being right here. That's supposed to be a circle, not a. Okay, there you go. And of course, this is elliptical, not circular, but that still means the velocity is tangential to the path. So I'm drawing the velocity tangential to the ellipse, not necessarily perpendicular to the radial vector. Now we also have the r vector, which is the vector that points from the sun to the actual planet. That's going to be like that. And in fact, that direction is our radial direction. And what you see is there's an angle between the r vector and the v vector. So this is the r vector right here. The velocity vector is right here. And we're going to say that this angle right here is phi. Okay. Now, if you allow a little bit of time, then the r vector will change from where it is to a slightly different location, and that means the planet's going to be in a slightly different location, and that's a small, small, small change in angle, and that chases out sort of a crooked pizza slice. In other words, the pizza slice that I'm talking about here looks a little bit like that. Okay. But what we're doing is we're taking it to be such a small amount of time, we're going to imagine basically that it's almost a right triangle, and that this being a right triangle says that the area here, which is the differential area, dA, is 1/2 base times height, because that's the formula for a triangle. So we're going to say dA is equal to 1/2 of the actual radius, because that's not going to change very much in that small time interval, times the height, which is v times delta t. But I need the component perpendicular, so in order to get the component of v perpendicular, I would break V up into V parallel and V perpendicular, and you'd see that V perpendicular is actually given by V times the sine of phi. So this is equal to 1 half R V sine phi times delta t. So we get dA over dt, the change in area per unit time, is actually equal to 1 half RV sine phi, like that. Now, if you talk about the angular momentum is L is equal to R cross P, and the magnitude of that angular momentum is R times M times V times the sine of the angle between the V and the R, which is the angle phi. So what we can see is R times V times sine phi is actually equal to the angular momentum divided by M. So now I can replace this with L over M. And when I do that, I get dA over dt is equal to L over 2M. But L is a conserved quantity, so L is conserved, which implies L equals a constant. And M, the mass of the planet, is a constant. So dA over dt, the change in area for a single unit of time, is equal to a constant. And that's really the equivalent of what we were trying to, is exactly the same as what we were trying to prove. Specific said use conservation of angular momentum to prove that the planet sweeps out equal areas in equal times. So an area over a time would give you one quantity. A different area over a different time should give you that exact same quantity. And therefore, that says that dA over dt should be a constant. We just proved that dA over dt is a constant. Again, this is where I would ask questions if anybody had any questions, but they don't. But we are done now. We've got example 1112 I want to do now. Example 1112 says a bullet strikes a cylinder edge. A bullet of mass m moving with velocity v strikes the and becomes embedded at the edge of a cylinder of mass big M and radius r0 as shown in figure 1122. The cylinder, initially at rest, begins to rotate about the symmetry axis, which remains fixed in position. Assuming no frictional torque, what is the angular velocity of the cylinder after this collision? So let me draw the picture. We're going to draw a little bullet, and it has a little mass v, or excuse me, a little mass m, and it has a velocity v. And it is aimed right for the edge of a large cylindrical mass like that. So this is actually a cylinder, which we might picture to be something like, ooh, that was not good. Okay, we'll leave that part alone because that turned out bad. But this cylinder has a mass of M, big M, and a radius R0 like that. Okay. So what we're asked to do is we're asked to assume there's no frictional torque and calculate the angular velocity after the collision. So this is initial, but then final will be the following. I'm going to actually borrow that same circle here. Say copy, say paste, and put it right here. Only now this thing is rotating with some angular velocity omega is equal to question mark. Now, what we know is I it for a cylinder is 1/2 m r squared. In this case, it's 1/2 m r zero squared. But this is the final case. And in this case, we not only have the mass of the cylinder, we also have a mass of a small bullet, M, smeared sort of around the edge right at R equal R. So the angular momentum initial, L sub I, is going to be equal to just, remember how we did it before, it's L equals R cross P. So in this case, it's going to be M times V times R0. Not in that order. It would actually be R times MV0 when we do the cross product. But in this case, we're just talking about the magnitude. But afterwards, we're going to have L final is equal to I omega for the little mass plus I omega for the big mass, but the two omegas are the same. So the I in this case is going to be M R0 squared for the little mass. And then the moment of inertia for the cylinder is going to be 1/2 m r0 squared. And then all of this is going to be multiplied by omega because they're all stuck together moving at the same velocity. So now we can say conservation of angular momentum, Li equals Lf. Notice we are saying the system is the little mass m and the big cylinder m, so that, yeah, there's a huge force and torque applied to the cylinder as a result of the bullet, and a huge force applied to the bullet as a result of the cylinder, but those are all internal forces. So since the cylinder is mounted on a nearly frictionless axle, we should have conservation of angular momentum because the net torque is zero. With that in mind, we're going to say MVR0 is equal to MR0 squared plus 1/2 big M R0 squared. All of that times omega, and the omega is what we want here. We can see that a common factor of R0 can come out of everything. And now we can say that omega should be equal to MV divided by MR0 plus 1/2 big M R0, like that. So that is the final, or that's the angular velocity right after the collision. And that's part of what we were asked to do. And now what we're supposed to do is we're also supposed to find, it says, assuming no frictional torque, what is the angular velocity of the cylinder after this collision? And is kinetic energy conserved? What we need to figure out is what is the kinetic energy before and after. So kinetic energy initial is just 1/2 little m little v squared. And what is the kinetic energy final? Well, kinetic energy final is 1/2, and it's 1/2 I omega squared. So in this case, we get 1/2, and then times I is going to be MR0 squared plus 1/2 MR0 squared times omega squared. And omega squared, of course, is that omega that we just calculated, but I'll just say right there that's omega squared. Now what we want to do is figure out what they are. So let's go ahead and plug in this quantity for omega, and that gives me 1/2 MR0 squared plus 1/2 MR0 squared times M squared V squared over MR0 plus 1/2 MR0. And this might be a good time to reintroduce the R0s that we calculated, just because I have the R0s in the bottom. So I'm going to multiply the top and bottom by R0. Okay, and in so doing, that's going to allow me a little bit of freedom to do something nice algebraically speaking. So this is going to be 1/2 MR0 squared plus 1/2 MR0 squared. And then this is going to be M squared V squared R0 over, oops, I think I need to multiply it by squared. Yeah, that should be by R0 squared. No, no, just a single one would be fine. So let me kill that right quick. Okay, so that's going to be that. Now, when I distribute this in, it's this quantity in the bottom has to be squared as well. And I actually never put that squared up there, so I need to do that now. Let me go ahead and put that like that, and then I'll write these parentheses around there in purple. So this is going to be m r0 squared plus 1/2 m r0 squared, and that whole quantity is going to be squared. So I already had one of the R zeros in there, and now it just added the other one. So yeah, that's good. Now, the reason why I did all that is because you can see now that this denominator matches this numerator, so I can get rid of this 2 and get rid of that completely, and that's going to give me 1/2 m squared v squared R0 over excuse me, over m R0 squared plus 1/2 m R0 squared like that. So that's K final. Now I can say K final minus K initial is equal to, there's a common factor of 1/2, so I'm just going to pull that out in front. And this is going to be m squared v squared R0 over m R0 squared plus 1/2 big M R0 squared minus, now the other term was just m v squared like that. I think it's pretty obvious that these are not equal, so that's really what they ask, is whether kinetic energy was conserved, but we can find out specifically what they differ by. Your book does all this algebra. I'm going to try to show you as much of it as we can, given the time. We got about 14 minutes left. So the 1/2 is just going to stay out in front, and I'm going to get a common denominator. This is going to be m squared v squared R0. All of this is going to have a common denominator of m R0 squared plus 1/2 big M R0 squared. And this minus here is going to be the mv squared times that same denominator. So I'm going to get m squared, because it's m times m, times R0 squared times v squared. Minus, that minus has to be distributed because the fraction bar is also a grouping. So the minus is going to be in the second term as well. And this is going to be 1/2 m R0 squared. In this case, we have the 1/2 m R0 squared, and we have the v squared as well. So that's really what we're getting in this result. So I still have the 1/2 out in front, and now I can see, is the m squared v squared times R0, is that acceptable? M squared v squared times, why does one of them have m squared v squared R0 squared, and the other one I only have m squared v squared R0 instead of R0 squared? So there's some error in somewhere where I must have supposedly had a m squared v squared R0 squared instead of a m squared v squared R0. Let's see. So final minus initial m squared v squared. Is the units on the first term in the curly bracket, does that actually match? I got m squared v squared R0, and then I just got mv squared on the other one. But I've got m R0 squared in the bottom, so that makes it m v over r. So no, I think I'm actually supposed to do that as a R0 squared. I might have dropped a R0, or I should have multiplied. There was one point where I sort of slipped up and thought I should have multiplied by R0 squared over R0 squared. That might have been the case. and that looks like it is the case now. In order to get the R0 in there, that would have just made one of up. Yep, that's exactly what it was. So these, when I wrote this R0, that was supposed to be a squared, and that was supposed to be a squared too. So to fix that, that one's going to make this one into a 2. So I put that in a slightly bolder exponent so y'all can see that I made the change. And then I'm going to change that there as well. And then I'm going to change that there and change that there. Now it works. So see I have m squared v squared r0 squared, again, minus m squared r0 squared v squared. So these two terms are going to completely cancel each other out. And I ultimately just get a negative sign because the term that's left in the numerator is a negative, and that's going to be 1 half m m r0 squared v squared, all of that over m r0 squared plus 1 half m r0 squared. And that's the difference in the, or that's the change in kinetic energy. So we can see the change in kinetic energy is not zero, so it clearly is the fact that the angular or the kinetic energy is not conserved. This is not an elastic collision. As you expected, it's looked a lot like uh, a totally inelastic collision because the two stuck together, so you would expect it to be different from that. And this actually showed that it is different. You could probably manipulate this and make it a little smoother. I'm not completely sure, but you probably could. And if you did that, maybe you'd get a little bit better. Your book ends up having negative mm. I'll just write down what they have. Let's say book has negative mm over 2m plus 4m. Notice that's a big M and a little m, and then all of that times v squared. So if anybody wants to figure out the algebra to get that answer, I'll take that as an extra credit for you folks, so you can do that. But that completes example 1112, and I believe that's the last of them. Yeah, we go into section 11.7, which is the spinning top and the gyroscope, and that teaches you something about precession, which is a important concept. In fact, that's the Earth precesses as well. That's, for instance, the reason that the Tropic of Cancer and the Tropic of Capricorn are no longer related to the zodiac symbols of Cancer and Capricorn anymore, because basically what happened is when we made up the pseudoscience of astrology, or when humans made up the pseudoscience of astrology, what they discovered is that the sun was actually in the tropic of, or excuse me, was in the constellation of Cancer when the sun was actually directly over that 23 and a half positive degrees of latitude, and when it was over the negative, or the southern 23.5 degrees latitude, it was in the constellation of Cancer. Well, since then, the Earth is tilted back because of its precession, such that those are no longer accurate statements. And because of that, we still kept the Tropic of Cancer, the Tropic of Capricorn, but you can't just say that, well, we know for a fact that the sun's going to be in the constellation of Cancer on the summer solstice and in the constellation of Capricorn and the winter solstice. That's no longer the case, and that's also why our horoscopes don't necessarily match. I'm supposed to be born in June on June 3rd, and that would suggest that I was supposed to be a Gemini. But if you actually look up using an astronomical program, you'd find that the sun is not in the constellation of Gemini on the day I was born. It was actually, I think, in Taurus, if I remember correctly. All that's because of the precession of the Earth. So this precession is a important thing, but you're not required to know anything about it for my tests. And even the equations and stuff they give you, those are very interesting. I highly recommend you read it and learn it, but I'm not going to test you on it. And then the next section is rotating reference frames, inertial forces. I'm not going to cover that either, but that also introduces us to the Coriolis force. And I'll say the only thing I want you to know about the Coriolis effect is, one, it's not a real force. It's part of an acceleration term that would be on the right-hand side of Newton's second law. But if you write it on the left-hand side, it looks like a force. But in general, what what we can say about the Coriolis effect is that in the northern hemisphere, things deflect to the right, and in the southern hemisphere, they deflect to the left. So if you imagine a low pressure zone in the northern hemisphere, what normally happens is winds automatically flow from high pressure to low pressure. That means all of these winds would all head directly towards the low pressure zone that would be otherwise something we recognize as a thunderstorm or hurricane. And I'm trying to draw these the same length, but obviously I didn't do that well, but it doesn't matter too terribly much. I'm just trying to show basically that all the winds sort of come in this way. But because of the Coriolis effect, all of these winds are going to be reflected to the right. So this wind, in fact, is going to go this way. This wind is going to go this way. This one this way. This one this way. This way. And this way. And this way. And this way. So all of these winds are going to end up circling around in a counterclockwise fashion. And that is the direction of hurricanes in the northern hemisphere. There's also frictional effects that take into account, but mainly we can see that the actual fact that a hurricane winds go counterclockwise around the low pressure is a result of the Coriolis effect. I'm not requiring you to know anything about that. I'm just telling you as a educated citizen, that's what you can know about the Coriolis effect. So I should probably at least write down the word Coriolis. So Coriolis, it might help if I write with something other than an eraser. Coriolis effect. Things in northern hemisphere deflect to the right. And another way you can think about that, remember the Earth, for instance, is rotating uh, this direction. And you might imagine, for instance, the United States goes something like this. There's Texas. Well, actually, I drew it a little too far south. I was trying not to put the nastiness of a hurricane right on the United States, I guess. So this is roughly like the United States, and now you can get some idea. But for instance, if you just try to randomly fly, for instance, from let's say from north to south, or excuse me, from south to north, if you're flying that direction, then as you can tell, if you just set your airplane to fly due north, the Earth is actually rotating under you like that, and in fact, you're going to tend to actually land a little bit west of north. And that can be understood in terms of the Coriolis force as, oh, the Coriolis force caused this, when in actuality, it was just a fact that the Earth rotated under you. So, anyways, that's something else you can use the Coriolis force for. But that's it. Have a good day, everyone. Normally, I would wait here till the last person leaves in case anybody had any questions, but no one said anything about that and no one showed up. So we're free to go. Have a good day. Bye bye.